This video is about L'Hopital's rule in indeterminate forms. This is our second video. In the last video, we introduced L'Hopital's rule and talked about how to evaluate 0 times infinity indeterminate forms. And we're going to start this video by reviewing all of that, and then we will discuss these topics. We're going to look at the exponential indeterminate forms, 0 to the 0, infinity to the 0, and 1 to the infinity, and talk about how to address those. We'll also talk about eliminating infinity minus infinity indeterminate forms. And then we'll look at some forms that look indeterminate but happen to be determinate. We actually know what the result should be just by looking at the form. Although sometimes it doesn't look like that on the surface. So we're going to get to that briefly, but let's start by reviewing L'Hopital's rule. So L'Hopital's rule says that if the limit as x approaches c of f of x over g of x is a 0 over 0 indeterminate form, or a plus or minus infinity over infinity indeterminate form, then this limit is equal to this limit. So all you have to do is take the derivative of the numerator and the derivative of the denominator separately and evaluate this limit instead. Now this notation can be changed slightly. Here we're assuming c is a finite number, but c could be positive infinity or negative infinity. We could approach c from the left or the right, and all of those limits. And this still would hold with that change of notation. So the idea is if you have a 0 over 0 indeterminate form, or a plus or minus infinity over plus or minus infinity indeterminate form, instead of evaluating your original limit, you can evaluate the limit of the derivative of the numerator over the derivative of the denominator. And the reason that is true is because we're looking at rates of growth. We're looking at how one function compares to the other in the race to approach 0 in the 0 over 0 case, or in the race to approach infinity in the infinity over infinity case. Now these are the only times you can use L'Hopital's rule. You have to have one of these quotient forms, infinity over infinity, plus or minus infinity over infinity, or 0 over 0. If you don't have one of those quotient forms, if you have a 0 times infinity indeterminate form, and you're wondering, does that one approach 0 faster than that one goes to infinity? Then we get 0. Does that one approach infinity faster than that one approaches 0? Then we get infinity. They approach at basically the same rate, so we get a number. We cannot evaluate the limit in that form, but if we rewrite the product f times g as f over 1 over g, or g over 1 over f, well, that's equivalent to this. And if this was an infinity times 0 indeterminate form before, when you write it this way, that'll be infinity over infinity. If f was approaching infinity and g was approaching 0, we get infinity over something, then this something is 1 over something very small, so that will approach infinity or negative infinity. And so you have the infinity over infinity type here, and if g was originally approaching 0 and f was originally approaching infinity, you have 0 over 1 over something very large, which is something very small. So this is 0 over 0, and this is infinity over infinity, provided that this was originally infinity times 0. So writing that product in one of these ways gets you to one of those forms. And then once it's in this form, you can use L'Hopital's rule. Now in this video, we talk about how to handle exponential indeterminate forms. So here are the 3 types. We could have a 0 to the 0 indeterminate form. So you've got a function in the base and a function in the exponent. They're both functions of your variable. Let's say your variable is x. If the base is approaching 0 while the exponent is approaching 0, well, there are some possibilities here for what that limit could be. If this base approaches 0 faster than that exponent approaches 0, I'll have 0 raised to some power, and 0 raised to some power is going to give me 0. Now, if this exponent approaches 0 before this base gets to 0, so I have a number raised to the 0 power, I'm going to get 1. So the question is it 0 or is it 1? Or if they approach at the same rate, what happens? We'll figure out how to evaluate that. But when if through direct evaluation of the limit, you just substitute the value of x or t or whatever your variable is, if you get 0 to the 0 power, that's an indeterminate form. That means there's more work to be done, and I'm going to show you what work needs to be done to get rid of that indeterminate form and figure out what your limit is. Infinity to the 0 power is an indeterminate form for pretty much the same reason. We want to know, does this approach infinity faster than this approaches 0? If it does, we've got infinity to some power. It's going to be infinity. If the exponent approaches 0 faster than the base approaches infinity, we'll have a number raised to the 0 power, so we get 1. And then maybe in that race to approach their limiting values, well, they're approaching at the same rate, then we might get some number in between. And something similar happens here. If this is just truly a 1, I've got 1 raised to the infinity power, I get 1. But if I have a function that's approaching 1, and the exponent is approaching infinity, this is indeterminate. So let's say I'm approaching 1, and the exponent is approaching infinity, and my base approaches 1, gets close to 1 faster than that gets to infinity. So if then I'll have 1 raised to some power, and 1 raised to some power will be 1. Now, if our function in the base is approaching 1 from above, so it's a number that's larger than 1, and the exponent approaches infinity faster than the base approaches 1, then I'll have a number larger than 1 raised to an infinite power, so I'll get infinity. Now, if the base is approaching 1 from the other side, so it's approaching 1 from numbers smaller than 1, so it's a proper fraction. If that's happening, and infinity, or in the exponent approaches infinity faster than the base approaches 1, we'll have that proper fraction raised to a very large power, and so we'll get 0. So we could get 0 here, we could get infinity, we could get 1, who knows what's going on. So that's what makes that indeterminate. All 3 of these are handled in basically the same way, and we'll talk about that in a second. And then there's one other indeterminate form. That's the infinity minus infinity indeterminate form. We've got 2 functions. We've got one that's going to infinity, the other one that's going to infinity. You don't get 0. You're not guaranteed to get 0. It's not infinity minus infinity, it doesn't just cancel out. If this function approaches infinity faster than this function does, well, then we get infinity for our limit. If this function approaches infinity faster than this one does, well, then we get negative infinity for the limit. And if they approach infinity at about the same rate, you might get a finite number, which seems odd. And that number may be 0. That number may be 20, which is a little odd, but we'll talk about how to handle those as well. And then we'll look at some determinant forms. So let's talk about the exponential indeterminate forms. Here's your approach. If you have an exponential indeterminate form, so it's one of those 3 types, this is how we'll do it. I always let y equal the limit. So we have a given limit that we're trying to find. It's one of these exponential types. So we let y equal the limit. And we're trying to get rid of that exponential form. So we're going to take the log of both sides. I usually use the natural log. Some people like to use the log base 10. It really doesn't matter. The whole point of taking the natural log of both sides is to be able to rewrite that exponential function as a product. So you take the log of both sides, and then you use the fact that natural log of a to some power is that power times natural log of a to rewrite that expression. So you're going to take that exponential and you're going to end up writing it as a product because you can bring that exponent down if you have the log of that there. And then generally at this point, we had 0 to the 0, or infinity to the 0, or 1 to the infinity. In all of those cases, after you bring that exponent down, you're going to end up with a 0 times infinity indeterminate form. So you've rewritten the expression, and then you'll have to rewrite again using this technique that we talked about earlier for addressing the 0 times infinity indeterminate form. So you're going to rewrite that as a 0 over 0 indeterminate form, or plus or minus infinity over infinity indeterminate form, using that algebraic manipulation that we talked about in the last video. Finally, you'll be able to apply L'Hopital's rule. And that will give you the natural logarithm of the limit that you're looking for. And then you'll use the exponential to solve for the limit. That's a lot of steps. It's easier when we see them in action. But the basic idea is right here. You're going to let y equal the limit, take the log of both sides, then you're going to use this log property to rewrite your expression, and eventually you're going to solve for y. That's the plan. Let's do it. So here's our first example. We have the limit as x approaches 0 from the right of x raised to the square root of x power. So I ask myself, well, what happens to the base and what happens to the exponent as x approaches 0 from the right? Well, the base is approaching 0. As x approaches 0 from the right, that's the square root of a tiny positive number. Square root of a tiny positive number is also a tiny positive number. So this is a 0 to the 0 indeterminate form. Question is, does this approach 0 faster or does that approach 0 faster? Do we get 0 or do we get 1? Or do they approach at the same rate and we get some other number? Well, since we have an exponential type indeterminate form, after we identify it as such, then we will let y equal the limit and compute or take the log, take the natural log of both sides. Okay, so we said, let's let y equal this. And then we'll take the log of this side and set that equal to the log of this side. Now the logarithmic function is a continuous function, so you can actually pull that limit out. So the natural log of this limit is equal to the limit of this natural log. That's legal because of the fact that this function on the outside is continuous. Okay, so now I've got log of something raised to a power. So we want to use this log property to rewrite that expression. If you have a constant times natural log of a, that's the same as natural log of a raised to that power. So if you have a power inside, you can bring that out front. That's what that rule says. So we can bring this square root of x out front. So we still have natural log of y, and y is what we're looking for, is equal to the limit as x approaches 0 from the right of the square root of x times natural log of x. And that's because we just brought that square root of x out front using this property. All right? We always do that. That's how we handle all of the exponential type indeterminate forms. So we're a little bit closer. We don't have exponents anymore, which is very good. But now we've got this times this, and we want to evaluate this limit. Well, square root of x still approaches 0. And remember, natural log of x goes to negative infinity as x approaches 0 from the right. Remember, this is what natural log looks like. As x gets close to 0 from the right-hand side, x is getting closer and closer to 0. The y's are going to negative infinity. The y's are getting very large in magnitude, but more and more negative. So that's a 0 times negative infinity in determinant form. Now, remember how we handle that. I need to rewrite this as a quotient. So I've got two options. I can either leave the natural log of x in the numerator and divide by 1 over the square root of x, or I can leave this in the numerator and divide by 1 over natural log of x. I think I'd like to leave my log in the numerator. So I've got natural log of x over here, and we'll divide by 1 over square root of x. And again, that's legal, because if I'm taking this and I'm dividing by this fraction is multiplying by the reciprocal. And the reciprocal of 1 over square root of x is square root of x. Now, after we do that, we should have an infinity over infinity, ignoring the sign, or a 0 over 0 indeterminate form. Now, as x approaches 0 from the right, natural log of x still approaches negative infinity. So we've got negative infinity in our numerator. And as x approaches 0 from the right, this is a tiny positive number. 1 over a tiny positive number is a large positive number. So that's a negative infinity over infinity as well. Okay, so now we can use L'Hopital's rule. So according to L'Hopital's rule, this limit is equal to this limit. You just take the derivative of the numerator and the derivative of the denominator, and you evaluate this limit instead. My numerator is a natural log of x. The denominator, that's an x to the 1/2. But since it's in the denominator of that fraction, it's an x to the negative 1/2. So we apply L'Hopital's rule here. So we rewrote our product in determinant form as a quotient, and now we applied L'Hopital's rule. And our hope is that when we're done, we won't have an indeterminate form anymore, and we can evaluate the limit. So I've got 1 over x over, the derivative of x to the negative 1/2 is negative 1/2, x to the negative 1/2 minus 1, that's x to the negative 3/2. And we could rewrite that this way, that 2 stays in the denominator, and we've got that x to the 3/2 in the denominator of that other fraction. So we still have an infinity over, looks like negative infinity indeterminate form, but this can be simplified algebraically. So let's just do some algebra. And our hope is that the algebra will get rid of the problem. So I've got that fraction in the numerator, I leave it alone. I'm dividing by a fraction, so I flip it and I multiply. and the x's reduce, you can subtract the exponents. And that's -2. 3/2 minus 1 is 1/2. So we get -2 times x to the 1/2, which is a function that's continuous as x approaches 0 from the right. So we just get -2 times the square root of 0, which is 0. Okay, now that is not our answer. We did all of that and we did not get the answer yet. The answer was y. Y was the limit as x approached 0 from the right of x raised to the square root of x power. That was this. We said, let's let y equal this. And our goal was to find y. So right now we've got natural log of y. Natural log of y is equal to 0. So now we have to solve for y. To get rid of that natural log, we exponentiate, because the natural exponential function and that natural logarithmic function, they undo each other. They're inverse operations. So we get y equals e to the 0, and e to the 0 is 1. So what does that mean? It's a limit as x approaches 0 from the right of x raised to the square root of x is 1. Let's think about it. That was a 0 to the 0 indeterminate form. We said if this base approaches 0 before the exponent approaches 0, we should get 0. If the exponent approaches 0 faster than the base does, then we should get 1, because we'll have a number raised to the 0 power. So it looks like this one must approach 0 faster than the square root of x approaches 0 faster than x approaches 0, because we got 1. Okay, so that's one example of that. Let's look at another example. Same idea, a new problem. Let's take the limit as x approaches 0 from the right of cosine of 3x raised to the 2 over x power. Well, let's take the limit as x approaches 0 from the right of the base and the exponent. As x approaches 0, this is the base is approaching cosine of 0, and cosine of 0, remember, is 1. So I've got 1 in my base. And as x approaches 0 from the right, this is 2 over a tiny positive number. 2 over a tiny positive number, that's going to be a large positive number, so we have a 1 to the infinity indeterminate form. So first we recognize that it's indeterminate, and then we let y equal this limit, and then solve for y. So we want to let y equal the limit, and then we're trying to get that exponent out of the exponent and out here as a factor. In order to do that, in order to get this x out of the exponent, we take the log of both sides. So we have natural log of y, so it's natural log of what we're looking for, is natural log of this limit. So many parentheses everywhere. So I'm just starting to use brackets. Now the natural log of the limit is the limit of the natural log. Because that log function is continuous, you can bring it inside. And then we say we've got log of something raised to a power. According to our log properties, we can bring that power out front. So log of a to the n is n times natural log of a. So we've got a 2 over x out front, and then we have natural log of cosine of 3 over x, or of 3 times x, excuse me. Okay, now we have to think about this, look at this, and think about what happens to this factor and this factor. As x approaches 0 from the right, this goes to infinity. And as x approaches 0 from the right, cosine of 0 is approaching 1. Natural log of 1 is 0. So this is an infinity times 0 indeterminate form. And actually, this is a great candidate for writing it as infinity or 0 over 0. This is already written as a fraction. So let's just write this log as itself over 1 and multiply straight across. That should do the job. That should give us a 0 over 0. So we have natural log of y equals the limit as x approaches 0 from the right of 2 times natural log of cosine of 3x, all divided by x. And natural log of cosine of 0 is natural log of 1. Natural log of 1 is 0. So this is a 0 over 0 indeterminate form. That's great. That means we can use L'Hopital's rule. Now at this step, you can just write out the limit as x approaches 0 from the right of the derivative of this over the derivative of this. I think I'm going to skip that step this time and just go ahead and take that derivative. So I've got 2, and then I'm taking the derivative of this numerator, and I've got an inside function, cosine of 3x. The derivative of log of a function is 1 over that function times the derivative of the inside by the chain rule. And the derivative of cosine of 3x, that requires a chain rule as well. The derivative of cosine of a function is negative sine of that function times the derivative of the inside, and the derivative of 3x is 3. And I'll write those as fractions. So that's the derivative of our numerator. It required using the chain rule twice. And the derivative of the denominator, derivative of x, which is just 1. Now, I didn't write that 2 as a fraction, but that's a 2 over 1 times this fraction times this fraction times that fraction. Now, if I multiply straight across and think of that as a 2 over 1, I'll get negative 6 times sine of 3x all over cosine of 3x. And a lot of students make the mistake of differentiating again. Always make sure you check. Once you've got that simplified, you say, is that a 0 over 0 indeterminate form again? Or is it an infinity over infinity indeterminate form? Or is it a function I can take the limit of? Then I'll just take the limit and be done. As x approaches 0 from the right, sine of 0 is approaching 0. So that numerator is approaching 0. The denominator, that's cosine of 0, that's 1. So we have 0 over 1, and we get 0. Okay, so natural log of the limit that we were looking for is equal to 0. So now you just want to solve for y. Now it's just coincidence that the limit happened to be 0 in this example and the last example. The e and the log undo each other, and we get y is equal to e to the 0, which is 1. Or in other words, we've just proven that the limit as x approaches 0 from the right of cosine of 3x raised to the 2 over x is 1. So this base is approaching 1. That exponent was approaching infinity. So I guess this was approaching 1 faster than that was approaching infinity. So I ended up with 1 raised to some power, and 1 raised to some power is 1. Okay. Let's do one last example. We've seen the 1 to the infinity indeterminate form. And the first example we looked at was a 0 to the 0 indeterminate form. Let's look at the last one. That the limit as x approaches infinity of x raised to the natural log of 2 over 1 plus natural log of x power. And that's an odd looking one. And remember what your log function looks like, how it behaves. As x approaches 0 from the right, it goes to negative infinity. As x goes to infinity, it slowly grows to infinity. Remember, rate of change is 1 over x. So it's always growing. It's growing slower and slower all the time. For every x value, it grows a little bit slower. Okay. So taking the limit as x approaches infinity of this, I want to know what happens to the base and the exponent. If the base approached 2 and that exponent approached 0, we would just get 2 to the 0, which would be 1. We would be done. It's not indeterminate. But if it's one of our indeterminate forms, we've got more work to do. As x approaches infinity, the base approaches infinity. Let's see what happens to the exponent. Now, natural log of 2 is just a number. In the denominator here, you've got 1 plus natural log of x. Natural log of x is slowly growing to infinity as x goes to infinity. So this is natural log of 2 plus something really large. A number over something really large is something really small. So that's it's an infinity to the 0 indeterminate form. If you're saying, why is that determinate again? If the base approaches infinity faster than this approaches 0, we might get infinity. If the exponent approaches 0 faster than the base approaches infinity, we might get 1. If the base approaches infinity at the same rate that that approaches 0, we might get some other number. So we've got more work to do. So every time you've got that exponential type indeterminate form, you let y equal the given limit, and then you take the natural log of both sides. So you have y equals the limit as x goes to infinity of x raised to this power. And then we say, okay, let's take the log of this side and set that equal to the log of this other side. So log of y is equal to the log of the limit as x approaches infinity of x raised to this power. And then since the log is a continuous function, you can pull that limit out. The log of the limit is the limit of the log. And then you see why we do this. The whole point of taking the log of this is to be able to use this exponent property. We know that log of a to the n is n times natural log of a. So we can bring that exponent out front. And then we'll just have a natural log of x over there. So this becomes the limit as x approaches infinity of the exponent times log of x. Now right now, we know that the denominator is going to infinity. So we've got 1 over something very large, it's just something very small. So we get 0 there. And then as x goes to infinity, natural log of x goes to infinity. So we have a 1 or a 0 times infinity indeterminate form. This pretty much always happens with these exponential type indeterminate forms. Once you take the log of the base, you get something that's approaching either 0 or infinity. And then this other factor approaches the other thing to make it indeterminate. So we're here, and we need to rewrite it as a fraction. Since this one's already a fraction, the easiest way to write this one as a fraction is to just multiply straight across. And our hope is that when we do that, we'll have either infinity over infinity or 0 over 0. And we do have infinity over infinity. Natural log of 2 is just a number. This is approaching infinity very slowly, so is this. Hope you guys can see that these are going to approach infinity at the same rate. I've got a constant times natural log of x, and then I've got a constant plus natural log of x. So really what's changing as x goes to infinity? It's just the natural log of x. Pretty sure that the limit's going to be natural log of 2 for this, but we'll see. We see that it's infinity over infinity, so we can apply L'Hopital's rule. So you take the derivative of the numerator, you take the derivative of the denominator and divide. Natural log of 2 is just a constant. The derivative of natural log of x is 1 over x. The derivative of 1 plus natural log of x is the derivative of 1, which is 0, plus the derivative of natural log of x, which is 1 over x. See what I mean? We just get the natural log of 2. Okay, that's great. So that is not our answer. We're very close to getting our answer. We're looking for y. Y was this limit. We let y equal that limit, and we took the log of both sides so that we could evaluate the limit, so that we could get that function of x out of the exponent. But we're still not done. We're trying to find y, and right now all we have is natural log of y. We know that natural log of y is equal to natural log of 2. To get rid of those logarithms, you use the base e. E to this power equals e to that power. The natural log and that natural exponential function undo each other, and you get y equals 2. So that means that the limit as x goes to infinity of x raised to the natural log of 2 over 1 plus natural log of x, that's 2. Because that's what y is. Y was that limit. So remember what we started with. We started with an infinity to the 0 indeterminate form. That's what this is. We said if this gets to infinity before that gets to 0, we should get infinity. If this gets to 0 before that gets to infinity, we should have a number raised to the 0 power, which should be 1. Now if this approaches 0 at the same, or this approaches infinity at the same rate that this approaches 0, then we might get some other number other than infinity or 1. It turns out that this approaches infinity at the same rate that this approaches 0, and we get 2. Or about the same rate, so we get 2. So it's pretty cool. All right, so we've seen the 3 exponential type indeterminate forms and how to handle them. We just let y equal the limit, take the log of both sides, use log properties to simplify, eventually evaluate the limit using L'Hopital's rule, and then we use the exponent to get rid of that log to solve for y. Okay, so that's how we handle that. Now the next type of indeterminate form is this infinity minus infinity indeterminate form. So let's look at a problem like that. let's say we have the limit as x approaches 1 of x over x minus 1 minus 1 over natural log of x. Okay. Let's think about if this is even indeterminate. Okay. So x is approaching 1. That means I've got a negative 1 over a natural log of 1 here. So that's a 1 over 0. So that's either going to be positive infinity or negative infinity. Let's look at the graph of natural log of x again. Y equals natural log of x looks like that. As x approaches 1, the y values on that graph approach 0. Now, we have to be careful because we're dividing by something that's getting close to 0. So we're actually going to have different values for this limit on the left and on the right. So let's think about this as x approaches 1 from the right, and then let's think about it as x approaches 1 from the left and see what we get. As x approaches 1 from the right, I'm approaching from the right-hand side, the natural log of some number that's slightly larger than 1 is going to be a tiny positive number. 1 over a tiny positive number is going to be a large positive number, and so I would get infinity there. Now let's think about this quotient. As x approaches 1 from the right, I've got a 1 over 0, so it's plus or minus infinity. But to figure out the sign of that, we need to look at the sign of the numerator and the sign of the denominator. Well, the numerator is approaching 1, so this is definitely positive. As we approach 1 from the right, so we're on this side of 1. So let's say x is 1.001. From the right, this x minus 1, that's going to be a tiny positive number. So I've got a 1 over a tiny positive number, which is a large positive number. So I have an infinity minus infinity indeterminate form. If this one gets to infinity faster, we could get infinity. If this one goes to infinity faster, we could get negative infinity. If they approach infinity at the same rate, maybe we get 17. Who knows? Okay, so that's what happens from the right. Now let's think about what happens from the left. Now from the left, as x approaches 1 from the left, the natural log of x approaches 0, but it's a tiny negative number. See the y values are below that x-axis, so they're tiny negative y values. So this is 1 over a tiny negative number. 1 over a tiny negative number is a large negative number. So I've got a negative 1 times something that's going to negative infinity. So I'm subtracting negative infinity here. So it's like I'm adding infinity. Okay, let's think about what happens to this as x approaches 1 from the left. As x approaches 1 from the left, let's say x is 0.99. I get 0.99 minus 1. So that's a tiny negative number. So I get a 1 divided by a tiny negative number. That's a large negative number. So I have a negative infinity plus infinity. That's an indeterminate form as well. So when they gave us that original problem, the limit as x approaches 1 of this, whether we approach from the left or the right, we get an indeterminate form, either infinity minus infinity or negative infinity plus infinity. So, okay. Still doesn't help us solve this problem. Let's go back to the original question. Just needed to check and see if it was an indeterminate form, and it turns out it is. Whether we're on the left or the right, it is. Okay. The way we tend to handle this, the infinity minus infinity or negative infinity plus infinity, is if you have fractions, and we're very fortunate we do, we want to get a common denominator here. And then our hope is after we get a common denominator, it'll be one of these types and we'll be able to use L'Hopital's rule. Doesn't always happen, but our hope is that that happens. So let's make a note of that. To eliminate the infinity minus infinity indeterminate form, you're going to try to write that function that you're taking the limit of. You've got the limit as x approaches c of f minus g, or f plus g, and you have this, they have the opposite signs, something like that. You want to write this differently. And the goal is to write f minus g as a product or a quotient somehow. Now this time we had two quotients to begin with, so we're in luck. We can get a common denominator and write that as a single quotient. So the least common denominator of these two fractions is just the product of those two denominators. They don't have any factors in common. So in order to make this equal to the least common denominator of x minus 1 times natural log of x, I need to multiply by natural log of x over here. That's legal as long as I also multiply by natural log of x in the numerator. That's not going to change the value of my fraction. It's just going to write it in a different form, or represent it in a different form. So that's totally fine. Over here, in order to make this my denominator, the natural log of x is already there, but the x minus 1 is missing. So we'll multiply by that x minus 1 over itself. And so we've got that. All right. And now you have the same denominator. So you can just subtract the numerators. We've got x natural log of x over here minus the quantity x minus 1. I think I'll distribute that negative. That negative times that x and that negative times the negative 1. It's going to give me a negative x plus 1 there. Okay, so it's a quotient. That's great. Maybe it's an indeterminate form, or maybe it's a limit we can just evaluate. Let's see. As x approaches 1, question is what happens to the numerator? Well, natural log of 1 is 0, so that's 0. So we have 0 minus 1 plus 1, so we get 0 in the numerator. And as x approaches 1, this is 0. 1 minus 1 is 0 times natural log of 0. So we've got 0 times 0. So it's definitely 0. No matter how you look at it, that's 0. So we have a 0 over 0 indeterminate form. That's great. So that means we get to apply L'Hopital's rule. And L'Hopital's rule may get us one step closer to what we're looking for. So let's do this. I've got the derivative of x times natural log of x minus x plus 1 over the derivative of the quantity x minus 1 times natural log of x. To take this derivative, let's use the product rule. We have derivative of the first. My first function is x, so that's 1, times the second, plus derivative of the second. Derivative of natural log of x is 1 over x, times the first. And then we're done with that part, and we take the derivative of negative x, that's negative 1, and the derivative of 1 is 0. Cool. And then down here we do the same thing. Got a product rule. There's my first function and there's my second function. Derivative of the first times the second, plus derivative of the second, 1 over x, times the first. Okay. Those x's reduce. The 1 minus 1 is 0. And we just end up with a natural log of x in the numerator. And down here we've got a natural log of x. 1 over x times x is just going to give me a 1. And then I have a 1 over x minus 1 over there. So the question is, do we have an indeterminate form anymore? Let's see. As x approaches 1, I've got natural log of 1, which is 0. And then over here, I've got natural log of 1, still 0. 0 plus 1 minus 1 is 0. So it's still a 0 over 0 indeterminate form. But that's good. We can use L'Hopital's rule again. No big deal. Oops, I don't know why I put 0. Zero's on the brain, I guess. Derivative of natural log of x is 1 over x. The derivative of natural log of x there is 1 over x. Derivative of 1 is 0. And this, I want to think of as an x to the negative 1. The derivative of negative x to the negative 1 is positive x to the negative 2. So I've got 1 over x plus 1 over x squared. The question is this still an indeterminate form? Oh, it's finally not. If I plug in x equals 1, I get a 1 up here, and a 1, and a 1. So I've got 1 over 1 plus 1. So I get 1/2. So in this war between this function that's going to infinity and this function that's trying to go to negative infinity, it's like a tug of war. It's like, you get 1/2. I guess you had to compromise somewhere, or something like that. Okay. So our goal is, if possible, to write f minus g as a product or a quotient. If we're lucky enough to get a couple of fractions like this, we usually just get a common denominator. And let's do one more like that. I have the limit as x approaches 0 from the right of 1 over x minus 1 over arctangent of x. As x approaches 0 from the right, that's 1 over a tiny positive number. That's 1 over a tiny positive number is a large positive number, so we get infinity. And then remember what arctan looks like. We took one branch of that tangent function. We switched x and y. Tangent function had vertical asymptotes at x equals odd multiples of pi over 2. So when we took one branch of that tangent function, we switched x and y. Instead of getting vertical asymptotes, we got horizontal asymptotes. And so arctan looks like this. As x approaches 0 from the right, arctan approaches 0, so this is 1 over 0, which is either plus or minus infinity. Now, from our graph, we see that the arctangent values, those are the y values on our graph, those are tiny positive numbers as x approaches 0 from the right. So I've got 1 over a tiny positive number, that's a large positive number. So I've got an infinity minus infinity indeterminate form. And we've got a couple of fractions, so we can get a common denominator. And because these denominators do not have anything in common, the LCD is just the product of the two denominators. So I want this denominator to be x arctan of x. So I multiply by arctan of x over arctan of x. And that'll give me what I want in the denominator. Over here, I want the denominator to be the same as that. The only part that's missing is that x. So we multiply by x over x. And remember, the reason we do the same thing in the numerator and denominator is because all this is multiplying by a 1. We've got 1 times this function here. And 1 times a function is exactly the same thing. It's the same function, it's just written in a different form. So that's all we want to do is write this in a different form and then manipulate it. And then our hope is, after we do all of that algebra, that we get to a point where we can actually evaluate the limit. So now we've got a common denominator, so we can write this as a single quotient. And our hope is that when we do that, we can use L'Hopital's rule. So let's see what happens. This numerator is arctan x. That numerator is x. So as x approaches 0 from the right, we've got 0 minus 0 over 0 times 0. So this is a 0 over 0 indeterminate form. That's why we got a common denominator, and that's a great thing. Now we can use L'Hopital's rule. According to L'Hopital's rule, all I have to do is take the derivative of the numerator and the derivative of the denominator and take that limit instead, and it's going to give me the same result. Well, the derivative of arctan of x is 1 over 1 plus x squared. Remember, we proved that in class using implicit differentiation. Is it implicit differentiation? No, it wasn't implicit differentiation. I'm thinking of the wrong thing. It'll come back to me. Let's see. But we did. We found this result by letting y equal arctan of x. Yeah, I guess it was. Anyway, the derivative of arctan is 1 over 1 plus x squared. The derivative of x is just 1. Then over here, I've got a product, so I want to use the product rule. Derivative of a product is the derivative of the first times the second plus derivative of the second times the first. So we've got this now. The question is, do we still have an indeterminate form? Well, as x approaches 0, I get a 1 minus 1, so that's 0. And then I have arctan of 0 plus this, and if x is approaching 0, we get 0 plus 0. So it's a 0 over 0 indeterminate form still. But notice we've got fractions within fractions. We've got complex fractions here. If we clear the complex fractions, there's a chance that we could get rid of the 0 over 0 indeterminate form. It's also possible that it won't help, but we'll see. So we clear the complex fractions by multiplying by that denominator. And remember, the whole reason you're doing this is to just get rid of that denominator. Like, how can I get rid of it? Well, I'm dividing by it. To get rid of it, I multiply by it. And that's legal as long as I do the same thing in the numerator and denominator of my larger fraction. And you want to distribute. We've got two terms there. See that minus sign? That tells me I've got to multiply twice. That plus sign, you distribute. So you've got the limit as x approaches 0 from the right. This times this is going to give me a 1 minus 1 times that quantity. And then I have 1 plus x squared times arctan. And this times this, those fractions will reduce and we'll just be left with an x. Do I still have a 0 over 0 indeterminate form? I do. But at least I don't have complex fractions. And let's distribute that negative. So then I'll have 1 minus 1. Those 1s will reduce. We just have a negative x squared in the numerator. That's at least pretty simple. If I take the derivative twice, that x squared will be gone, so that's hopeful. Gives me some hope that the end is in sight. So right now, this is a 0 over 0 indeterminate form. Let's take the derivative again. Use L'Hopital's rule. The derivative of the numerator is negative 2x. And then to take the derivative of the denominator, call that our first function and that our second function, and use the product rule. We get derivative of the first times the second plus derivative of the second times the first. That's convenient. And then we have to add the derivative of x, which is 1. Those guys reduce. Get some 2's everywhere. That's nice. We can factor that out. So I've got 2x times arctan of x, and then 1 plus 1 is 2. So let's factor out the 2. I'm just happy every time something reduces. Gets us a little closer to our result. Okay, question is this indeterminate? If I plug in x equals 0, what do I get? 0 over 1. Ta-da! That's determinate. 0 over 1 is just 0. So in the tug of war between these two functions, they're equally matched. No one wins. And it looks like nobody budged or went anywhere. Got 0. Okay. So that is how we get rid of the infinity minus infinity indeterminate form. So this video was about two different types of indeterminate forms. We had these exponential types. In those cases, we let y equal the limit, take the log of both sides, use this fact to get that function of x out of the exponent. And then we have to use a lot of algebraic manipulation and eventually L'Hopital's rule to evaluate the limit. And then you're going to have natural log of what you're looking for, natural log of y is equal to some number, and you just solve for y using exponential properties. So that's what we do for these guys. And for these guys, if you're so lucky that the two functions are fractions, and most of the time we are, get a common denominator, and then the hope is that when you get a common denominator, you'll have a 0 over 0 indeterminate form or a plus or minus infinity over infinity indeterminate form. Now, I promised you we'd talk about some determinant forms that look indeterminate. So say you've got a function and you're adding another function and both of them are approaching infinity. That's not indeterminate. What's a large number plus a large number? It's a large number. So don't try to get a common denominator or anything. It's not necessary. Those two numbers, when you add them together, you get infinity. If you have a negative infinity and you're subtracting infinity, that's a large negative number minus a large number. It's still going to be a large negative number. You get negative infinity. Now this one is a little harder to see, but if you have the base approaching 0 and that exponent going to infinity, it turns out you're going to get 0 every time. And if you have 0 raised to the negative infinity, you can think of that as 1 over 0 raised to the positive infinity. And since 0 to the positive infinity, that always results in a 0, you end up with 1 over something that's approaching 0. So 1 over something that's approaching 0 is plus or minus infinity, depending on whether this is approaching 0 from the right or from the left. So I guess this is somewhat indeterminate in the sense that you're not really sure if you get positive or negative infinity, but it's not indeterminate in the sense of I have no idea how it's going to behave. I do know I'll get one of the infinities. The question is which one. In order to figure out which one, I need to analyze the sign. So if you see something that looks like these as you're evaluating limits, just go ahead and be done with it. L'Hopital's rule is not necessary. L'Hopital's rule is necessary if you have a 0 over 0 indeterminate form, or plus or minus infinity over infinity. If you have 0 times infinity or 0 times negative infinity, you want to rewrite that product as a quotient. Instead of multiplying by g, divide by 1 over g. And then that will allow you to write something like this, like one of these guys. Then we've got the 0 to the 0 indeterminate form, infinity to the 0, and 1 to the infinity. With all of these, you let y equal the limit, take the log of both sides, use log properties to get the exponent out of the exponent and out front to write it as a product. And then you're going to do algebra to get something that looks like this into something that looks like this, and eventually you'll have natural log of y equals some number. Solve for y. And then the last type we looked at is the infinity minus infinity. So these are indeterminate forms. These require L'Hopital's rule. These don't. As you're using L'Hopital's rule, remember, always, always, always check to see if L'Hopital's rule applies before you apply it. I can't tell you how many times I've had students do something like this. Take the limit as x approaches, let's say, infinity of e to the x over x cubed. And they're like, oh, that's an infinity of over infinity indeterminate form. So let's take the derivative. And let's take the derivative again. And let's take the derivative again. And let's take the derivative again. Of course, you don't want to divide by 0, but you get the idea. L'Hopital's rule applied here and here, because that's infinity over infinity. That's infinity over infinity. That's infinity over infinity. This is infinity over 6. So this step is not legal. Even though it got you the right answer, this limit happens to be infinity. You don't want to just keep differentiating forever. You can only use L'Hopital's rule when you still have that infinity over infinity indeterminate form or the 0 over 0 indeterminate form. So at every step, every time you get to a limit, you should check. Substitute in that value of x and see what happens to the numerator and denominator. If they're approaching 0 over 0 or plus or minus infinity over infinity, go ahead and use L'Hopital's rule again. If not, finish the limit, and then you're going to be very close to being done, if not finished with the problem. So that is how we handle indeterminate forms.